Chapter 7.7 is the midpoint and the trapezoidal rule. Now, we're almost taking a step back because the midpoint and trapezoidal rule, we're going back to approximating the area under a curve. We already know how to find the perfect area under a curve. So the perfect area under this curve from A to B is the definite integral from A to B of whatever function we have, dx. Remember what this meant? This is the height. It was basically derived from the height times the base of rectangles. So it's base times height. As the base gets infinitely small, so my delta x gets extremely, extremely small, so that my height is just the function itself. And this is my function. So this will equal to the perfect area. We're taking it a step back because to find the perfect area, we actually have to know the antiderivative of f of x, right? Sometimes we actually can't find the antiderivative of f of x, not without a calculator at least. And that is where we want better approximations to this area than the LRAM and the RRAM, the left-hand rectangular area method and the right rectangular area method. So midpoint and trapezoidal rule are area approximations. They are still approximating. The midpoint rule is still a rectangular method, so we're actually going to call it the MRAM, the midpoint rectangular area method. Trapezoidal rule is obviously not rectangular, it's a trapezoid, so we're just going to keep calling it the trapezoidal rule. All right, so let's start with the MRAM, the midpoint rectangular area method. So here we have some sort of a curve, and we still have some boundaries from A to B, right? And we're going to cut it into n rectangles. Rectangles, I'm going to choose it to be 4, for example. So I'm going to cut right down the middle this way. Again, it's the 4 that I want to cut first. So here we have our delta x, and our change of x, our delta x, is going to be the base of our rectangles. So let me name it the base. Is my delta x, it's going to be b minus a, which is this distance here, divided by n. In our case, it is 4. All right? Now for the height of my rectangles, instead of LRAM, I would cut the left-hand side and make that output the height. RRAM would make the right-hand output the height. This time, the MRAM, naturally, I'm going to make the midpoint the height of my rectangle. Now, when you do this, you should be able to see almost immediately, this is a really good example, of why this is a better approximation. Take a look at this second rectangle here. If I did an LRAM, it would have been an overestimate. I would have gone way above the curve. If I did an RRAM here, I would have done a severe underestimate, right? Where this part of the curve is sticking out. The MRAM kind of averages out both over and under estimates this way, okay? So it's a slightly better approximation. It's a way better approximation if your ends are going to be limited in this regard. Okay? And the more ends we have, of course, as we take n to infinity, that will become the perfect answer. Okay? But in this case, MRAM is definitely my most, on average, the most accurate rectangular approximation. So now let's take a look. The height is going to be an f. It's going to be f of the midpoint, which we're actually going to call that. It's kind of the average, and then of whichever rectangle we're talking about, whether we're talking about the first rectangle or the second rectangle, the third rectangle, fourth rectangle, so forth. Now the way that we describe that is going to be, well, a is an x value, correct? So I'm going to make a equal to x naught so that I can have x sub 1 for this input right here. X sub 2 is what we're going to call that one. X sub 3, and b will be the same as x sub 4 Okay, so that way we can vary it to varying depending on however many ends. So the average of this, the midpoint is going to be the average of x naught and x sub 1. All right, so x naught plus x sub 1 divided by 2. So the way that we're going to, we can write it as f of x sub I plus 1, or x sub I guess, minus x sub, sorry, plus, it's the average, minus 1 all over 2. Okay, that's going to be the midpoint. Right, so it's going to be x sub I, the first rectangle, first x input, minus 1, okay, divided by 2, plus 1 divided by 2. All right, so now therefore the MRAM will be just the summation of all of those rectangle areas. So from I equals 1 to however many rectangles we want, of the base, which is delta x, times the height, which is the output of the midpoint of whichever rectangle we are talking about. Okay, so that is my MRAM. Now let's talk about our trapezoidal rule. Now our trapezoidal rule, when we were in geometry, so we're basically going to be summing up, adding up a bunch of area of trapezoids. Now in geometry, our trapezoids almost always went like this, typically, right? We didn't call these, we called these the two parallel sides, we called them base 1 and base 2, and we always had to multiply that by the height somehow. The area of a trapezoid, if you don't remember, is 1/2. It's the average of the bases, base 1 plus base 2, times the perpendicular height. Now what we're going to do is we're going to rotate that trapezoid and make it look, we're going to start looking at it more like this, where the parallel sides are always going to be on the left and right. So base 1, base 2 here, we're always going to have a perpendicular height going this way. If this doesn't look familiar at all to you yet, well, it's going to look a lot like, if we cut it from A to B, and we cut it, let's say, into N trapezoids, what we're now doing is now, instead of cutting it horizontally straight across for a height, we're going to cut it from this point to this point, and we're creating a bunch of trapezoids. From this left output to this right output, cutting trapezoids this way and this way. Okay, so now our delta x will become this height. Okay, the height of the trapezoid is going to be delta x, and what we're doing is we're going to take the average of B1, the parallel base 1 and base 2 here, the two outputs on the left and the right. Now let's take a look at what that looks like. So let's use the trapezoidal rule. Okay, so the first trapezoid here is going to be 1/2 the average of the, well, it's going to be the average of the bases, which is B1 plus B2 divided by 2 times the height. So the very first one right here, the height, the 1/2 will stay the same. I'm going to multiply it by, let's multiply it by the height first, because that one's easy. It's going to be my delta x. Okay. Now the B1 plus B2 is going to be, this is going to be base 1, the output here, and then the output here will become base 2, which means we need to know what these values are. So we're going to go back to labeling them x sub 0, which is going to be equal to a. We're going to call this x sub 1, call this x sub 2, this input x sub 3, and b will equal to x sub 4, which is right there. So if that's the case, what we have here for the heights are going to be f of x sub naught, x naught, plus the second base right here, f of x sub 1, right? And that's going to be my very first area of this trapezoid. Now what we're doing next is we're going to add up the area of the second trapezoid, which is going to be, again, 1/2 times delta x, 1/2 times delta x, times this output plus this output. That 1/2 delta x is going to be the same for every single trapezoid, so I'm just going to pull that out right there. And so this one was for trapezoid 1. And for the second trapezoid, this one right here, I'm going to find f of x sub 1 plus f of x sub 2. That will be for the second one. And of course, that will be times delta x times the 1/2. We just factored it out. We're going to add it to the third one here, which will be f of x sub 2 plus f of x sub 3, f of x sub 2 plus f of x sub 3, plus, this will be for the third trapezoid, plus the fourth trapezoid right here will be f of x sub 3 plus f of x sub 4. Okay. Now in this case, we can simplify this. It will always become 1/2 delta x, right? And what you're going to be summing up, if you notice, f of x sub 1, f of x naught does not double up, but the rest of them on the inside do, and then the last one here also does not double up. So you have f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2 plus 2 times f of x sub 3 plus, does not double up, the last one, f of x sub 4. So let's sum up here. The midpoint rule, or the MRAM, took all the sum of all the rectangles. It's a sum of a bunch of rectangles, for which the base was delta x, and then it's the same for every single rectangle, so I can factor that out. And then I get f of x sub, well, the midpoint of the first rectangle, plus f of x sub the midpoint of the second rectangle, plus the midpoint of the third rectangle, up until the midpoint of the nth rectangle, right? The trapezoidal rule takes your 1/2, the height delta x, I can factor that out, and then I have f of x, the very first f of x naught, plus 2 times everything else in between, until the very last one where I don't double it up. Okay, so let's take a look at a quick example before I run out of time here. We want to find the integral from 1 to 2 of 1 over x dx. So I'm going to make it not to scale here, but I'm going to call this 1 to 2. If n is equal to 5, I'm going to split them up into 1, 2, 3, 4, 5. And then each of these will be 1.2, 1.4, 1.6, 1.8, which those will be our inputs. The very first one I'm going to find the MRAM for. And the MRAM will be delta x, which is here, which is 0.2. And then I'm going to add up each of these midpoints. So it's going to be f of 1.1, f of 1.3, f of 1.5, f of 1.7, and f of 1.9. So it'll be 1 over 1.1, 1 over 1.3, 1 over 1.5, 1 over 1.7, and 1 over 1.9. A quick way to double check that is going to be counting how many rectangles you have. I have 5. I should have 5. 1, 2, 3, 4, and 5. Which gives me approximately 0.691908. And I don't have enough room for the time for the trapezoidal rule, but you can find it in your book in chapter 7.7. The rest